Hello and welcome to lecture number 18. So today we are going to talk about the solid gas interface. So this is the last type of interface of the course. So before we have talked about the liquid solid interface and liquid interface. So today this is the time to spend some light on solid gas interface. So when we talk about solid gas interface, the most important phenomenon that appears is the process called adsorption. So remember, adsorption is also the rate determining state of the heterogeneous equilibrium. That means, the heterogeneous kinetics, heterogeneous catalysis. Means the catalytic reaction involving solid and liquid or solid and gas. So mainly the solid gas heterogeneous catalysis goes through the adsorption process, and that adsorption determines the rate of the catalytic reaction. So now coming back, the definition of the process adsorption. Say when a solid is in contact with a gas, so what happens that the gas molecules sometimes, or the gas molecules may undergo an interaction with the solid. And this interaction is essentially reversible. So that means what I'm going to say is when we have a solid surface and we have some gas molecules which are in contact with the solid. So it may happen that the gas molecule gets attached to the surface. So this interaction means the gas molecules is some kind of attachment between the gas molecules and the solid, and the gas molecules would physically get attached with the solid surface. So this process of attachment is called the adsorption. So remember, adsorption is basically a surface phenomenon. And so this is called adsorption. And the reverse process, so that means when the gas molecule gets detached from the surface, it is referred as desorption. Okay, so remember there is a P in both the words. So adsorption is with P and the desorption is also with P. Okay, so generically together the entire process, adsorption plus desorption together is basically referred as the process sorption. Okay, so sorption means both adsorption and desorption. So the thing is, what kind of interaction they would undergo? So they would undergo either some weaker van der Waals adsorption or van der Waals interaction, or they can undergo some strong bonding interaction like covalent bonding, chemical attachment. Alright, so based on the type of interaction, we can have two types of adsorption. So one is called the physisorption, and the another process is called chemisorption. And the difference of the two are pretty obvious. So the major differences between physisorption and chemisorption is something like this, that the physisorption is mainly a physical phenomenon. That means no chemical interaction is involved. So the bonding between the solid and gas is mainly based on the van der Waals interaction. All right. So van der Waals force. And for chemisorption is essentially chemical bonding. Could be covalent bonding. Most likely it's a covalent bonding. So the attachment is quite stronger in chemisorption and quite weaker in the physisorption. This is the number one. And the second difference is the physisorption always associated with some lower activation energy, and while in chemisorption is involved with higher activation energy. So this also tells us that since physisorption has a lower activation energy, the adsorption process in this manner achieves equilibrium faster. Here, the adsorption process takes time to reach the equilibrium. So these are the two primary differences now we can think of. Now there are some other differences for that too. Now in order to understand the other differences, we first have to focus on the thermodynamics of the adsorption. So the thermodynamics, if we think about in terms of delta G, so delta G is equal to delta H minus T delta S, where delta is the entropy change and delta H is the change of the enthalpy. Now if you look at the gas molecules before adsorption, so they are free in the air, so they have higher degrees of freedom, and but the moment they get adsorbed, they get attached to the surface, so their degrees of freedoms get compromised. So therefore, for adsorption process, so we can write for adsorption process, this delta S is highly negative. So since delta S is highly negative, so this term becomes a high positive value or positive value. So now in order to be for the adsorption process to be spontaneous, we want delta G to be negative. Now in order for delta G to be negative, delta H should be highly negative. And in negative in such a manner so it can surpass the T delta S, the high positive value. So therefore we can write here the delta H must be high negative value for the adsorption process to happen. So that means what? So delta G negative means this adsorption process is exothermic. All right. So exothermic process means it would release some energy once the gas molecules get adsorbed. So that also means that like any other exothermic process, so this exothermic process also gets facilitated at lower temperature. So this is true for any exothermic process. The process gets the process is more pronounced at a lower temperature. All right. So now if we come back to the differences of physisorption and chemisorption, there are two more differences that we can talk about. So one is it has the lower, so physisorption has lower or less delta, or you can see that we can write delta H is comparatively less negative, but it is negative so that the adsorption process becomes spontaneous. And for this one, the delta H is highly negative. Okay, so that is another difference. Now the last but not least, the major difference is that since chemisorption requires chemical bonding between the gas molecule and the solid, so every time the gas molecule needs to have contact with the solid. So therefore, this chemisorption is mainly limited within the monolayer adsorption. Means the gas molecules would essentially form a monolayer on the solid surface. So that is chemisorption. But in physisorption, the multi-layer adsorption is always possible. Now when we talk about the multi-layer adsorption, means so there will be one layer having direct contact with the solid, plus there will be multiple layer. That means some more gas molecules would be sitting on top of another gas molecules. But when the gas molecules are sitting on top of each other, so that would define a different phase, and that is almost equivalent to the liquefaction. And so the physical in physisorption, so the same van der Waals interaction would be valid when the gas molecule is directly interacting with the solid, or two different gas molecules are directly interacting with each other while getting absorbed. Okay, so these are the important points. So in physisorption, the van der Waals force of attraction is the sole most determining interaction, and it happens between gas and solid and also gas and gas, because it goes to the multiple layer. But in chemisorption, it is essentially monolayer. Alright, and the most striking feature that it has very high activation energy, and the reversibility and equilibrium is easily established here, and the equilibrium is not so easily established here because of the higher activation energy. Alright, so this is the major difference. But before we go to the next few terms that we have to define, we must tell that the entire process of adsorption is thermodynamically controlled. So it is not a kinetically driven phenomena. So this one we have to understand. Alright. So therefore, so I'm writing it once again, that the process of adsorption is thermodynamically controlled. Okay, so it is essentially reversible, number one, and number two, it goes through the establishment of instantaneous equilibrium at each and every state. Alright, so it goes through the equilibrium at every stage. Okay, so these are the major two considerations about the adsorption. Alright, so now proceeding further, there are one more term that we have to talk about. So probably you have come across the term called absorption isotherm. Okay, so this is nothing but a way of representing the data of the adsorption. So this is basically a graph plot. So absorption isotherm stands for the plot of the gas adsorbed. Okay, so essentially in terms of volume with respect to the applied pressure of the gas on the surface. So this is the pressure axis, this is the volume axis. So the pressure goes from very low value to high value, and whatever the gas volume adsorbed is plotted there. And then we generate a graph plot with some data point, and we may or may not have the points. But this is taken at a constant temperature. So T is constant. So if the T is not constant, the adsorption has no meaning, because we have already understood that from the thermodynamic consideration, and that adsorption process is meaningful only when, or adsorption process is spontaneous only when temperature, this is an exothermic process, and when the temperature is quite low. Low and temperature has to be constant. So therefore, since the temperature is constant for measuring the volume versus speed data, so that's why it is called, such type of graph plot is called the absorption isotherm. Isotherm means the same temperature. Alright, so next we will move on to some brief experimental description of how adsorption of a gas on certain solids are measured. Remember that analytical technique is a very crucial, helpful tool for the researchers uh, in order to understand the nature of the surface of a solid. Since we are studying colloids and surfaces, so measuring the properties of the surface, adsorption procedure gives a very important tool. Okay, so let's quickly take a look at this. So here I'm trying to describe a brief setup for experimental analysis of gas absorption. So what is there is basically the sample is taken in a tube, and we call it the sample tube. And the sample tube is connected with a gas reservoir as well as the high vacuum. All right. And in some part, during the some part of the gas tube, there is an outlet where the outlet is attached with the pressure detector. So let's talk about the very basic way that how the adsorption isotherm is obtained from a sample or from the interaction between the gas molecules and the sample. Here the analyte gas molecules is actually nitrogen. That means we are going to study the adsorption of nitrogen on some solid surface. So let's go into step-by-step process. The first step, that is the step 1, the process is called the degassing procedure. So what is the degassing procedure and why do we need it? Firstly, so let's assume that this is a surface, normal surface at room temperature, and also this is exposed in the environment. So at this condition, there are a lot of contaminants on the surface. So for example, there could be moisture adsorbed, that is water. There could be atmospheric carbon dioxide. Simply there could be some dust particle, or simply some aerial gas molecules are adsorbed, like at room temperature, maybe like oxygen, nitrogen, etc. Or maybe there is some chemisorbed gas already due to the present as a contaminant in the environment. All right. So basically the surface is occupied at the room temperature when it is not treated with anything. So we don't have enough free space for our analyte gas molecules to be absorbed. All right. So what we want this surface to be free of those unwanted gas molecules. So for that, what we do is actually we heat it up. We heat up the surface. Basically, we heat up the sample, solid sample, under high vacuum. Right. So the vacuum goes to almost 10 to the power minus 4 torr, and the heating can be maintained from there is a certain temperature range for which we can go up to. We can go from say 60 degree to 400 degrees Celsius. There is a wide temperature region. So we select the temperature based on the solid, because in too much high temperature, some sintering may happen, or some modification of the solid surface may happen. So therefore, the temperature should be optimum, but it is definitely higher than the room temperature. The higher, the better. So if we treat treat that surface in that condition, we have now the free surface. So we call this thing as the degassed surface or degassed sample. Alright, so now this sample is ready to take on fresh nitrogen or analyte molecule for adsorption. So the first step is degassing. So what it is done, it is the tube is connected with the high vacuum facility. So the high vacuum should be on at the first step, and vacuum should be connected with the tube. So the gas molecules, means the already adsorbed gas molecules, should go away at higher temperature. Alright. So the next step, the step number 2, is actually the adsorption process. So in the absorption process, what happens? So firstly, if we know that the degassed situation has arrived, we have to stop the vacuum. So that means it is under basically high vacuum, and we have disconnected the vacuum for working further. And then what we have to do is now we have to open the gas reservoir for absorption. But before that, I told you that now the temperature was raised, okay, at 100 degree or more. So the temperature has to be cooled down to a lower temperature so that absorption process is facilitated. So usually that lower temperature is taken as the liquid nitrogen temperature. So that means before the opening of the gas reservoir, the entire sample tube, including containing the sample, has to be dipped in a liquid nitrogen container. Okay, so there will be a thermoflask basically, and so those thermoflasks contains liquid nitrogen. So gradually it is lowered to the liquid nitrogen container and the top portion is filled. So now this entire gas tube is under liquid nitrogen, and some time is allowed so that the temperature inside the sample gets equilibrated with the liquid nitrogen temperature. So the liquid nitrogen temperature is basically 77 Kelvin. So all the absorption experiment is usually are usually carried out at the 77 Kelvin. And then slowly this gas reservoir's valve is open. All right, so the gas from the reservoir actually comes down and gets to interact with the solid surface. So, but you see here in the reservoir, there are two types of gases. One is the nitrogen and is the helium. So the role for helium is nothing, but it actually helps the nitrogen to flow. So it's helium acts as like a carrier gas in gas chromatography. So it has no role on the absorption. It just helps to carry the nitrogen gas from the reservoir up to the sample tube. And then some stipulated time is usually allowed. So it could be 4 hours, could be 5 hours, could be 6, and sometimes 8 hours, because it is thermodynamically controlled. So we don't care about time. We just care about that the gas should have sufficient amount of time to get adsorbed on the surface. So after the adsorption process is done, again there is another process, and this is also carried out, desorption, in order to prove or to see testing the reversibility of the process. So that means if we allow the gas to desorb, so the absorption data and desorption data on the isotherm should retrace each other, and that would be the proof of the reversibility. So, or that would be the proof that the desorption process is reversible. So what we actually do in the desorption process, we actually take away the liquid nitrogen content, obviously, because the desorption process has to be done in a higher temperature, not at the liquid nitrogen temperature. So the temperature is once again raised for desorption process. So it raised slightly more than the room temperature, and again the gases would starts to get dissolved, and how much gas is getting dissolved, it is once again detected from the pressure detector. So this is basically the summary of how this entire process is done. All right, so the data we get from this experiment is in this manner. That is the volume adsorbed. Okay, so the volume adsorbed is actually measured from these detectors. So there are various detectors which can detect not only the pressure but the volume that gets adsorbed. So volume adsorbed is usually given in cc, cubic centimeter, and it is usually expressed as in the standard temperature and pressure, means 0 degrees Celsius temperature and standard pressure, right? Means 1 atmospheric pressure, and versus the pressure. Okay, so this pressure is usually uh, represented or usually reported in P over P naught value. So that means it's a fraction. So what is P naught? So P naught is actually the saturated or saturation vapor pressure of the gas. So that means whenever if we slowly increase the pressure of the nitrogen on the sample in the sample chamber, so there will be a point. There will be a point coming, and the point is called the condensation point. That means the pressure of the nitrogen is almost equal to the saturated vapor pressure of the gas at that temperature. So next, the nitrogen is on the verge of being liquefied. So that pressure at the pressure at which it happens, it is called the saturated or saturation vapor pressure. So that means it cannot hold any more gas molecules. So next, if we increase the pressure a little bit, all the gas molecules would condense as liquid on that surface. So that is called P naught. So it is, and then P is the actual pressure of the nitrogen gas. So P by P0 actually can start from 0 and it can go up to 1. So the maximum value is 1 when P is equal to P naught. So therefore P by P naught value is a fraction. And therefore we can actually report that adsorption isotherm like this. So here we have P by P naught value, and it goes from 0 to 1, and we have volume adsorbed in cc, volume in cc at STP, standard temperature and pressure. So this is usually how the machine gives you the data, and then here you will get a data that is volume over P by P naught. Okay, so this is how so these are the little technical details of the experiments that are involved to carry out or to measure the or follow the adsorption procedure of the gas on solid. All right. So our next topic is once we get the data, all right, so how to interpret it. So can we explain by any theoretical model, or is there any way to predict how the data will come from some theory? So of course we have to learn a little bit about the theories that can explain the adsorption isotherms of gases on solid. So that we typically study as our next topic. Okay, so let's do that. So among the few theories that at the beginning started to explain or attempted to explain the adsorption behavior, Langmuir's theory was one of the most important and most prominent theory. So Langmuir was awarded Nobel Prize much later for his fundamental work or the pioneering work on the surface or surface properties. Anyway, so he first introduced his theory in 1916, long back, more than 100 years ago. And in those times, what people used to observe that common adsorption of common adsorbent and common adsorbents. So the common adsorbents were either activated carbon or activated charcoal, and the gas they used to study mostly are nitrogen, ammonia, etc. So in those days, such type of adsorption isotherm plots were available and were known. So the V versus P over P naught data points used to increase first, and then it used to flatten out with increasing pressure. So Langmuir attempted to explain this kind of experimental outcome from a theoretical perspective. So he initially assumed few considerations, a few statements. So I have listed it here one by one, so you can read it easily. So I will not go through each and every one of them, but most major assumption, or most important assumption Langmuir made was he assumed that the adsorption is confined to the monolayer only. That means only one layer of gas molecules are getting adsorbed on the surface. And so there are other assumptions, like the molecules don't interact with each other, or they don't roll over on the surface after getting adsorbed. And all adsorption sites are equivalent, means there is no site preference for the gas molecules while sitting on the surface. And then there is a term theta, which is defined as a fraction of site occupation, which is equal to the number of gas molecules adsorbed divided by the total number of possible adsorption sites. So then Langmuir started with the same thermodynamic consideration, that is the adsorption process is thermodynamically controlled and proceeds via establishment of equilibrium at each and every stage. So basically, if we think about the microscopic picture, so this is the gas molecules getting absorbed slowly. So we have this picture, okay? So that means forward direction is absorption and backward direction is desorption, and the adsorption is limited only up to the monolayer. So according to Langmuir, obviously, since this is a thermodynamically controlled, so rate of adsorption should be equal to the rate of desorption at any point. All right. So what is the rate of adsorption? So the rate of adsorption becomes actually depends on the rate constant of adsorption. So let's assume K ad stands for the rate constant of adsorption, and then it is dependent also on the pressure of the gas molecules. That is simply P. That means the higher the pressure is, higher will the tendency of the gas molecules to interact with the surface. So it depends on the pressure, and then it is also dependent on the fraction of sites that are unoccupied on the surface. That means the more number of empty spaces are there, the rate of adsorption will be faster. So that means the empty spaces are measured as a fraction. So this is 1 minus theta, because theta is the fraction of site occupied, and that is equal to the rate of desorption, air desorption, multiplied by definitely theta. Theta is the fraction of gas occupied. That means more the occupation, more will be the desorption rate. And here also Langmuir introduced another factor, that is e to the power minus EA divided by RT. So this EA is the activation energy of the desorption process. All right. So this term e to the power minus EA RT is almost like the exponential term of the Arrhenius equation. So it means the more the activation energy of desorption, the rate of desorption will be smaller, and the higher the temperature, the ambient temperature T, the desorption process will be faster, because it is e to the power of minus EA over RT. All right. So now if we try to solve the theta from this equation, so this is the basic equation, very simple. So if we try to solve the equation of theta, all right, like this, so we will end up with the term something like this, that is K desorption multiplied by P divided by, we have K desorption multiplied by P plus we have K adsorption and e to the power minus EA divided by RT. So you can try that out to see whether you end up with this. All right. So now the same thing can be expressed if we divide K adsorption on both numerator and denominator. So we are dividing both numerator and denominator by, so K adsorption. So this should be K desorption. So if we do so, we have P divided by P plus we have K adsorption divided by K desorption e to the power minus EA divided by RT. Okay, and that is equal to theta. So I'm going to erase the board here once again, and I'm going to write theta is equal to this here, and then Langmuir assumed one constant, that is the constant is called B. So B stands for K adsorption divided by K desorption e to the power EA divided by RT. So here this K adsorption divided by K desorption, this is nothing but the equilibrium constant of the adsorption. So this is K equilibrium of adsorption. So we can write K equilibrium adsorption e to the power EA divided by RT. So that is equal to B. So of course, if we include the constant B in this equation, then the theta takes up the shape of P divided by P plus this becomes 1 over B. Alright. So the moment theta becomes something like this, so this gets converted into BP divided by 1 plus BP. So where B is a constant, alright, and then B stands for where B is equal to K equilibrium of adsorption multiplied by e to the power EA divided by RT. So that is actually so this equation theta is equal to BP divided by 1 plus BP, where B is expressed as something like this in terms of equilibrium constant of adsorption and the activation energy of desorption is known as the Langmuir's equation explaining the adsorption of gases. Alright, and this equation is also known as the Langmuir adsorption equation, because with this we can easily explain this graph plot. Because if we try to draw theta versus P, alright, so something like this. So theta, although theta is a fraction of site occupancy, increasing theta means the increasing volume of gas absorbed. So theta and V are almost equivalent, and they are equivalent in fact. This is a way of this representation. And once again, if we divide P by P naught, it becomes the same thing. So if we theoretically plot theta versus P, so you see the curve would look like something like this. Alright, so now there are B values, right? So we can have different drawings for different B values. So we can draw this thing with B3, B2 and B1, and you can see here if we take the theoretical values like B3 greater than B2 greater than B1, you will generate this kind of graphical representation. So the Langmuir's equation actually now means at that time Langmuir equation was able to explain theoretically the outcome of the experimental behavior of adsorption on many common cases. Alright, and and this type of graph plot is also referred as the Langmuir's adsorption isotherm, alright, which is basically fitted following this equation. So the question now arises that although Langmuir was able to explain this kind of adsorption isotherm, how far Langmuir's theory was good. That means, is Langmuir's theory applicable to all the types of different adsorptions we see for different sets of gases on different types of solid surfaces? And is there any was there any problem or flaw with the Langmuir's assumption? All right. So for that, I think we need our next lecture session to address the strengths and weaknesses of Langmuir's theory and how other scientists overcame the Langmuir's weaknesses while explaining the absorption. Alright, so we will see that in the next lecture, that is lecture number 19. So stay put. I will see you in the next lecture. Till then, goodbye.